Okay, and welcome to Lecture 12, Chapter 13, Section 2. I'm going to be talking about percent composition, how that will get us to the empirical formula, and how we can get from there to the chemical or molecular formula. We really only use this for molecular compounds, partly because for ionic compounds, the empirical formula and the actual chemical formula are the same. But let's not go into too much detail there. All right. So first up, percent composition. Okay. This is also a mass percent, meaning that you have, for any particular element, x, x1, element 1, the percentage for x1 is equal to the mass coming from that element divided by the mass for element 1 plus the mass for element 2 plus, and so on. Okay, it's just, what percentage of the total mass comes from, that particular element. It's not particularly complicated. So, for example, you have water, H2O. Total mass of a water molecule is 18.02 atomic mass units, or, you can think of it as 1 mole is 18.02 grams. Either way, you'll get the same thing. Now, the amount of the mass coming from hydrogen is 2.016. The mass coming from oxygen is 15.999. I'm going to go ahead and do some rounding here just to save myself a little bit of time, but this is 2 over 18 versus 16 over 18. So 1/9 and 8/9, or 11.1% and 88.9%. Now, that one was particularly easy, mostly because there were two elements and they happened to round very, very nicely to whole numbers. That isn't always the case. And you don't often have to find the mass percentage for a compound, using math like this, unless you're a chemistry teacher coming up with examples for use in lecture or problems to put on a test. Normally, the way you find percent composition for an unknown compound is you burn it. You light that sucker on fire. I'm being quite literal here. You have, your open flame, and you have your sample burn and it gives off, fumes. And then you pass those fumes through a series of collectors. Each one is capable of trapping, a different element. And that's how you determine this. Well, I should say it's catching CO2 and H2O and NO2 and things like that. It's catching the products of the burnination. So it wouldn't catch oxygen in that way. They have specific detectors for every element. Nowadays, though, we have slightly better ways of doing this, more expensive ways. If we were going to do this in lab, you'd be playing with fire, not with the $25,000, $40,000 piece of equipment known as a mass spectrometer. So, let's go ahead and talk about the next bit. Getting from percent composition to empirical formula. This is what they had to do, and this was, one of the steps once upon a time when they were finding the chemical formulas of things. All the tools they had were fire, pretty much. And so they made use of it. Now, the way you do this is fairly straightforward. Well, yeah, I'm just going to stick with fairly straightforward. You should know by now that I'm a dirty, rotten liar. So you start with your mass percentage. And let's work with a particular example. We have 39.99% carbon, 6.713% hydrogen, and 53.28% oxygen. Now, these might not add up to exactly 100%. That's just, rounding errors. It happens. Now, the first thing you do is turn it into grams by just say, okay, if we had 100 grams, how much would we have of each one? And that's really, really easy. 39.99% of 100 is 39.99 grams. 6.713 grams, 53.28 grams. Easiest math you'll ever do. Slightly harder is you have to convert it to moles, which means you have to divide by the molar mass, or the atomic mass, because we're looking at elements. So that means you flip over to the periodic table. And first up we have carbon, which is 12.011 grams per mole. So divide by 12.011 grams per mole. This one we're going to divide by 1.008. So 1.008 grams per mole. And oxygen is 15.999. 999 grams per mole. And when you do that, the numbers you get are, for carbon, you get 3.33 moles. For hydrogen, you get 6.66 moles. And for oxygen, you once again get 3.33 moles. You may have already spotted the pattern here, but the next step, divide by, that's clearer, divide by the smallest number. So you have to divide by the smallest number. In this case, that's 3.33. It showed up twice. So you divide by 3.33, divide by 3.33, divide by 3.33. That gets you 1, 2, 1. This is a fairly simple and straightforward example because that means that the empirical formula is CH2O. And that's where we have to stop for this particular problem because I didn't give you the last bit of information necessary to get the chemical formula. And this empirical formula, it's going to be true for CH2O or C2H4O or C3H6O or any other multiple of this guy right here, the CH2O. They all have 39.99% carbon, 6.713% hydrogen, 53.28% oxygen. So you do need that additional bit of information. But there can be a difficulty. I'm going to go ahead and show it to you right now. Here's an example from a compound I made up. Okay, so it has carbon, hydrogen, nitrogen, and oxygen. And it is 40.66% carbon, 8.532% hydrogen, 23.72% nitrogen, and 27.09% oxygen. All right, so the first thing we do, we convert to grams. I mean, you can literally just cross out the percentages and replace them with grams. Then we divide by the molar mass of each element. So divide by 12.01 grams per mole, 1.008 grams per mole, 14.01 grams per mole, and 16.00 grams per mole. And what that gives us is 3.386 moles, 8.464 moles, 1.693 moles, and 1.693 moles. A couple of things I want to point out here. Hydrogen, nitrogen, and oxygen are all diatomic elements, meaning that in their molecular forms, it's H2, N2, and O2, Brinkelhoff. So in their molecular forms, the molar masses are 2.016, 28.02, and 32.00 grams per mole. We're not using those because we're not working with the elements, the pure elements in their pure state. We're dealing with a compound. So we're dealing with a whole bunch of atoms of hydrogen, nitrogen, and oxygen. So we use the atomic masses. The other thing I want to go ahead and emphasize is that even though hydrogen contributed the least to the mass, in terms of mass percent, it has the largest number of moles. That was true last time as well. Then carbon contributed the most, but it's in the middle. And nitrogen and oxygen had middling amounts for the mass, but the least amount for the number of moles. So you can't make any sort of assumptions about the empirical formula just based on the masses. You have to convert to moles. Otherwise, you're going to get all hooey. All right, so the next thing we do is we find the smallest number of moles. Nitrogen and oxygen are tied there. And we divide all of them by that. So they're all being divided by 1.693.
Young and lovely, the girl from Ipanema goes walking in as she passes it.
And one, do that. 1 and 1, and 2 and 4.999. Okay. You will see a lot of fractions for this. Rounding errors and so on is, the big part. So, you can just go ahead and round 4.999 to 5. But you will also occasionally see things like 3.33 or 1.5 or even, I suppose, 2.25. What that means is that you've got a fraction that you need to eliminate. Okay. So for now, let's just go ahead and stick with the fact that this is C2H5NO for the empirical formula for this one. And in a second, we'll talk about how to eliminate these fractions. And when I say in a second, I mean right now. So you need to learn to recognize which fractions refer to which decimals. Okay, so 0.5 means 1/2. 0.33 means a third. 0.66 would mean 2/3. 0.25 would be 1/4. 0.75 would be 3/4. And if you have something other than that, it means I've screwed up and given you the wrong sort of molecule. It's gone, way off the rails. It's, just ridiculous to assume that you should answer that. Or you've screwed up and you need to go back and check your math. Either one of those is possible. It's almost certainly you. But what this means is that you would get a ratio like, CH1.50, something like that. And obviously that's not kosher. That's not going to fly. You can't have half an atom. So you need to get rid of these fractions. You multiply by the denominator, the number on the bottom. Okay, so whenever you see a fraction like that, that means you're going to have to multiply the entire formula. Okay. So this case, it's times 2, meaning that the actual empirical formula is not CH1.50, it's C2H3O. Okay. C1.33, H1.5, O 2.25. just to, get them all out. You would need to get rid of each of these fractions. You're going to have to multiply the entire formula by the number necessary to get rid of each fraction. So first, let's go ahead and multiply by 3. That will get rid of this one here on the left. And that gives us C4, H4.5, O 6.75. You can already see this molecule is going to be kind of ridiculous. Now let's go ahead and get rid of this by multiplying by 2. That would give us C8, H9, O 13.5. Yeah. Let's go ahead and multiply by 2 again. We could have multiplied by 4 at the beginning. That would have resolved that and that at the same time. But multiplying by 2 twice is the same as multiplying by 4. So C16, H18, O27. Yes, this is an absurd molecule that I feel absolutely confident could never exist. Possibly. Almost definitely. It probably could, actually. Anyway, the point is, when you see a fraction, get rid of it by multiplying by the denominator of the fraction. And let's go ahead and move on to going from, let's see, we already covered percent composition, getting to empirical formula. Now let's get from there to the chemical formula. This is actually the easiest step. Okay, so C4H10. Well, it has an empirical formula of C2H5. And what you see is that this right here appears in the entire formula. So let's see, chemical formula, empirical formula, twice. Okay, it shows up in there twice. There are 2 of these. So another way to say is that you have C2H5 and C2H5, the 2 formula units. Remember, I've mentioned those before, talking about ionic compounds. So they have 2 formula units in the molecular formula or chemical formula. So the way you find that, given the information we have, is you will also need molar mass. Okay. So let's take a look at our previous examples. Our first example, we came up with an empirical formula of CH2O. And I can tell you that its molar mass is 60.05 grams per mole. Now, what we need to do is find the mass of the empirical formula, or you can call it the empirical mass. This is just like finding the molar mass or the formula mass for a chemical formula. It's just that you're doing it for the empirical formula. So C is 12.01, 2H is 1.008 times 2, and O is 15.999. And you just add those 3 numbers together. And what you get is 30.02 grams per mole. Now you just take the molar mass divided by the empirical mass, and that's going to get you a whole number N. In this case, 60.05 divided by 30.02 is equal to 2. Again, just rounding errors, which means that the chemical formula is equal to 2 formula units, or twice the empirical formula. So CH2O plus CH2O is C2H4O. In this case, the example molecule was vinegar. or acetic acid. Two different names for the same compound. Now, another example would be EF of CH2O with a molar mass of 180.15 grams per mole. And yes, this is the exact same empirical formula as acetic acid, but it's not acetic acid. It's not vinegar. Okay? So it has the same empirical mass, 30.02, and 180.15 grams per mole divided by 30.02 grams per mole. Remember, it's molar mass over empirical mass equals 6. So that means that the molecular formula is 6 formula units, or 6 times the empirical formula. 6 units of CH2O. So you just multiply each of the subscripts by 6. This is one of the very rare occasions where you are allowed to change the subscripts. Okay, so it's C6H12O6. For those of you who don't recognize it, this is glucose, or just plain old table sugar. All right, now one last example that I'll go ahead and work for you, all the way through, from percent composition to molecular formula. So, percent composition, we have carbon at 74.03%. Let's go ahead and make that 4 a little cleaner. And then we have hydrogen at 8.699%, and nitrogen at 17.27%. So, step 1, grams. All right, now we divide by the molar mass. So, divide by 12.01 grams per mole, 1.008 grams per mole, and 14.01 grams per mole. And in terms of moles, what that gives us is 6.164 moles, 8.630 moles, and 1.233 moles. Now, the smallest number of moles we have present is this guy from nitrogen, so we divide them all by 1.233.
Je ne sais pas ce que ça remplace. Et derrière nous, c'est encore à l'ombre. Faut-il encore qu'on raconte que quelque chose nous revient? Faut-il qu'on soit...
That's the easy one. Remember what I said about rounding errors? They'll always show up. They're not always this easy to spot. They usually are this easy to spot. When you're looking at things that should be whole numbers or simple fractions, they should be easy to spot. It's when they're not that you know that something has gone wrong. So, in this case, our empirical formula is C5H7N, which gives us an empirical formula mass, or an empirical mass, of 81.12 grams per mole. And our molecular mass, our molar mass, our formula mass is 162.24 grams per mole. In this case, I'm not using a fictional molecule. It is, in fact, well, hopefully this should be obvious, but 162.24 divided by 81.12 is 2. It's C10H14 in 2. Our mystery molecule here is nicotine. Okay, That's all we're going to cover. That's the entirety of this this section of Chapter 3. I will see you again in the next video.